In the last two videos we've seen how a 2x2 matrix, or a 2x2 array of numbers, defines for us a geometric transformation of the plane. In this video we're going to look at how an m by n matrix can be interpreted geometrically. So what does m by n mean? So it's a rectangular array of numbers with m rows and n columns. This is an m by n matrix. I'll sometimes write by as times. Okay, so for example, A, B, C, D, E, F is a 2x3 matrix. So I always get confused about this because it's like the opposite way around from what I expect for some reason. But okay, so geometrically, what does this do? So the claim is an m by n matrix A gives us a map or a transformation from Rn to Rm. So remember, Rn is column vectors of height n with n entries. Rm is column vectors of height m. So this is, you should think of this as n-dimensional space and this is m-dimensional space. What is this map? Well, it's, as before, a vector v in Rn gets sent to the vector av in Rm. So we should think of v as like x1, x2, ... up to xn. It has height n. And av, well, we're going to define it in exactly the same way we define 2x2 matrix multiplication. So we've got this grid of numbers, a, b, c, ... up to something, and then d, e, f up to something, etc. And we're going to work our way along each row in the matrix and multiply this entry by this entry and add b by the next one, which is x2, plus ... until we get to this entry here. And remember, this is there are n columns, so there are n of these guys on the top row, so this is going to end up pairing with xn. And then to get the second entry over here, we're going to go to the second row and do d times x1 plus e times x2 plus ... all the way down. And because there are m rows, in the end the thing we get here has height m. Okay, so first of all, let's just do an example. Let's say we have A, B, C, D, E, F, G, H, I. These are just numbers. And V is going to be X, Y, Z. I could call it X1, X2, X3, but I'm just going to call it X, Y, Z. So if we multiply this out, we're going to get AX plus BY plus CZ going across and down, and then DX plus EY plus FZ, and then GX plus HY plus IZ. Okay, so that's an example of a 3x3 matrix acting on a vector of height 3 producing a vector of height 3. So for example, if you want something concrete rather than just A, B, C, D, E, F, etc., you could take cos phi minus sine phi. Sorry, that's a theta, isn't it? Not phi. Sine theta cos theta 0, 0, 1, 0, 0. So usually the convention for reading out these matrices is you start from this entry and you work your way across, and then as if you were reading a book. So I should have read it cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. It's a 3 by 3 matrix. Think about what it does. If I apply it to x, y, z, I'm going to get cos theta x minus sine theta y. I'm going to get x sine theta plus y cos theta, and I'm going to get z. So these first two entries we know from the first lecture, because this is just rotation in the xy plane. This z is just mapping to z, so what's happening, this is a transformation of three-dimensional space. It's fixing the z-axis, the vertical axis, and it's rotating the xy plane. This is x, this is y, and this is z, by an amount theta. Actually, maybe I'll do those two in red to show that's what happens after the transformation. So this is the angle theta. Okay, so this is a rotation about the z-axis by an angle theta. Okay, so you can imagine now you can write down 3 by 3 matrices that represent any rotation of three-dimensional space. They get quite complicated, but you know, that gives you a way of really mathematically describing rotations of three-dimensional space, which can be very useful if you're, I don't know, trying to model things on a computer in 3 dimensions. Let's do an example where m and n are not the same. Oops. Okay, so new page. So another example. This is going to be A, B, C, D, E, F, so 2 by 3 matrices. So if I have a 2 by 3 matrix, I need to feed it a vector of height 3. And if I do that, it's going to output a vector of height 2. Right, let's just check that's what I said before. I feed it a vector of height n, n is 3, and it outputs a vector of height m, m is 2. And does that make sense? Yes, ax plus by plus cz, dx plus ey plus fz. That's what we get. So for example, if we take 1, 0, 0, 0, 1, 0, this is taking a three-dimensional vector x, y, z, and it's returning x, y. So what does that do? That just projects away the z dimension. It's the projection. To the xy plane. What happens if we had a matrix the other way around, like if we did 1, 0, 0, 1, 0, 0 as a 3 by 2 matrix, right? So 3 rows and 2 columns. So for that to eat a vector, it would have to be a 2 vector, a vector of height 2, right? And then we get 1 times x, 0 times y, x, 0 times x, 1 times y, 0 times x, 0 times y. So what does this do? This is a bit odd, right? It's taking the point x, y, and it's mapping it to the point x, y, 0 in three-dimensional space. So, you know, maybe I should draw, here's the xy plane over here. So this is the domain of our map, right? This is where our vector xy lives. So maybe xy is this point here, and it gets mapped to the corresponding point in three-dimensional space with the same x and y coordinates at height 0. So this map is called the inclusion of the xy plane into three-dimensional space R3. Okay, so these maps, these matrices, if they're not square matrices, if they're rectangular like these two, you're actually changing the dimension of the space, right? You're mapping from a low-dimensional space into a high-dimensional space, or from a high-dimensional space to a low-dimensional space, like a projection. So you might wonder why we need matrices that are bigger than 3x3 matrices. If we live in three-dimensional space, why would we need more than 3 dimensions to play with? Well, for example, the theory of special relativity deals with time on an equal footing to space, and the transformations in terms of which you can phrase the theory of relativity, so-called Lorentz transformations, are actually 4x4 matrices that rotate time and space into one another. A slightly more prosaic example, if you're into stats, then like statistics, then you could represent all your data as a vector. Maybe you have many samples that you've taken of something, and each of those samples is an entry in a vector, and then you want to predict some other variable in terms of the samples you've taken, and that transformation may well be represented as a very large matrix, depending on the size of your sample set. I just want to do a couple more examples. So here's one. Let's take 1, 2, 0 going downwards, 1, 0, 1 going downwards. So this is a 3x2 matrix. 1, 1, 2, 0, 1, 0, 1. So think for yourselves, where does this map start and where does it go to? Right, it goes from R2 to R3. In other words, it takes a vector of height 2, it outputs a vector of height 3. If you feed it xy, it'll give you back x plus y in the first entry, 2x plus 0y in the second entry, and 0x plus y in the third entry. Okay, this is a map from R2 into R3. What does it look like? Well, it's hard to imagine what a map looks like, but at least we can try and imagine its image. In other words, the set of all the points in R3, all the points in three-dimensional space that get hit by a point xy in R2. In other words, the set of all vectors of the form x plus y, 2x, y. So what does it look like? It's going to be a plane in R3. So here's R3, coordinate axes x, y and z. Where does the x-axis go? So the x-axis is the set of points x, 0 in R2. So that goes to x, 2x, 0. Okay, so if I just set y equal to 0 here, I get x, 2x, 0. So that's where the x-axis goes. What does that look like in this picture here? Well, it's a vector whose x component is x, whose y component is 2x, and whose z component is 0. So it lives in the xy plane. I'll draw it in red. It goes 1 along the x-axis and 2 along the y-axis, for example, or it goes x along the x-axis and 2x along the y-axis. So it's something like this. Right, so it's the line that points in that direction. And x could be anything here, right? So it's the whole x-axis. So we get this whole line here. What about the y-axis? The y-axis goes to the set of points where x is 0, so y, 0, y. Okay, so that has the y coordinate being 0. Alright, don't get confused. This y here is in R2. The y coordinate in R3 is this second entry here, which is 0. So let me draw this one in blue. So y0, y, it has to be in the xz plane, right? Because the first and last entries are non-zero, and they have to be equal, so it has to lie on this line, z equals x. Okay, so that's the image of the y-axis. And if you want to know where all the other points in R2 go, well, you just have to kind of imagine. So here's one I drew while the video was paused. This is supposed to be like a plane. It's a bit difficult to draw. It's a plane in R3. It's these grey lines. And it contains this red line, it contains this blue line, and it's spanned by those two lines. They determine the plane. So that's what the image of this map, this transformation, looks like. Let's do an example of the other kind, so an example that goes down a dimension. Let's take 1, 0, minus 1, 0, 1, minus 1. This is now going to go from R3 to R2. It's going to eat x, y, z, and it's going to return x minus z, y minus z. So you can see whenever I do this, I'm trying not to do it by using a formula. I'm trying to do it by saying it's this entry times this entry, this entry times this entry, this entry times this entry, summed up, etc. Okay, so what does this map look like? Well, again, it's not so easy to draw, but if we imagine that it's projecting from three-dimensional space onto, let's say, the xy plane, then it's a kind of projection. So in other words, if we include this now as the xy plane in three-dimensional space, we can kind of visualize what's going on. The points x, y, 0 go to x, y, because the z is just 0, so they would stay where they are. The points on the z-axis, this vertical axis that I just rubbed part of off, they are going to go where? So 0, 0, z, well, let's just do 0, 0, 1. where does that go? That's going to go to -1, -1 in the xy plane. That's back here somewhere. Right, these axes go back some way. So that's back in the xy plane, back here somewhere. Okay, so this vector at height 1 in the z-axis, which is maybe this guy here, is getting projected down like that. So in fact, the way you can visualize this projection is, imagine rain is falling onto the plane in this direction. Oops. So it's all the rain is falling parallel in the same direction, and the projection is just taking you along a raindrop down. And what are these grey arrows I'm drawing? They're pointing as if they started at height 1. So they're starting at sort of 0, 0, 0, 1 and ending at -1, -1. So what is the vector that points from 0, 0, 1 to -1, -1, 0? Well, it has to go down 1, right? So the z component should be -1. It has to go back 1 and back 1 in the x and y directions. So it should be -1, -1, -1 in total. Okay, so remember, a vector is an arrow, and at every point I'm projecting in the -1, -1, -1 direction along that arrow in the -1, -1, -1 direction. And if I project in that direction, that's going to take me to the xy plane, and it's going to take the point x, y, z to x minus z, y minus z. That's how you should imagine this this projection. So this direction, this line, -1, -1, -1, has a name. So we'll come to this later in the course. It's called the kernel of the matrix. So the line through the origin in the -1, -1, -1 direction is called the kernel of our matrix. It's the line of stuff that gets squished to the origin. So it's like the direction in which our raindrops are falling if we're projecting along the rain. In fact, maybe it's better to think of it as light rays, because then the word projection really makes sense, right? You're projecting like a projector in a cinema. You're projecting along light rays. Okay, so in the next video we're going to talk about matrix multiplication. So far we've seen how to act on a vector using a matrix. Now we're going to see how to multiply matrices themselves.